Okay, hi everybody. So what we're looking at today on Thursday is kind of wrapping up this idea of figuring out the density of hand sanitizer from doing some sort of everyday kind of experiment with excuse me, everyday type materials. So what we're going to be looking at today is really what I'm going to do is just kind of walk through and give you a video solution about what I did for the lab, and then also kind of look at what AP wants when they're looking at something like this. So this is going to be important because, well, as of right now, as of April 2nd, we don't know what the AP test is going to look like in terms of AP Physics or really any AP classes. But traditionally, they have these experimental design type questions on them. We've been preparing for them throughout the year, and we want to get pretty good at them because they're difficult questions, and we want to figure out how we do them. So hopefully the experimental design portion is still on the AP test. We'll find out on Friday. But if it's still on there, then it's a good thing to practice because it's a good well, one, it's good to think about how to set up an experiment like this, and then two, it's helpful for this AP test. How can we get the most amount of points as possible? And then what I'll do is I'll kind of go through and get some of your guys' experiments and just make a Google form where you're just kind of talking and being like, hey, I like this part of this person's experiment. I don't like this part of this person's experiment. Just because it's important for us to be able to, one of the main things they say is, oh, your experiment should be, somebody should be able to replicate it after one read through. So we want to make sure we're being clear and we want to use our classmates' help to kind of judge that. So I'll pick a few at random. I'll pick some that I like that are good examples, and then we'll go from there. So we'll kind of critique those, and that's what I will get from you all. Is I will look at your Google form that you fill out about grading these your peer experiments, your peers experiments. Yeah. So what we're gonna do is I'm gonna shift over to this one, so you can just see that. You can't see me. But yeah, so I kind of want to walk through how to do this lab. I kind of talked about the setup yesterday. Um, Sorry, I'm drinking some Coke. I had an energy drink in the morning. Some Bang. It's got creatine in it, and I'm like crashing at the moment, so I need to get more caffeine in me. So if you hear me drinking caffeine, I'm deeply sorry. But orange vanilla Coke, it's good stuff. It hits pretty good. I endorse it. I'm not sponsored by Coke, but so what we're looking at is this first part where we're saying, okay, students perform an experiment to collect data that can be used to determine the density rho L of an unknown liquid. They have a tall cylinder containing the liquid and some cubes of different sizes but the same known mass that all sink in the liquid. They only have a meter stick and a stopwatch to take measurements. So even though I kind of frame this as like figuring out the density of hand sanitizer, it's really an AP question where they're just trying to figure out this mystery liquid. So this is actually an AP experimental design type question. And so the first thing they want you to do is describe a procedure the students could use to collect the data needed to create a graph that can be used to determine the density of the fluid, including the measurements to be taken and any steps to reduce experimental uncertainty. So I kind of said it in this preview this preview question yesterday, but I think it's really hard to figure out a procedure if we don't know what kind of data we need. So I think it's best to kind of think about your experiment, think about this with the end in mind. So think about what are you going to collect, what equations are going to use so you can really design a good procedure. So you can say, hey, these are the data points that I need, and these are how I'm going to get to those data points. So I'm going to do it in a way that makes sense to me. But the College Board kind of has another experiment. They're both very similar, but I just want to do my way so we can kind of incorporate the linearizing that we did on Tuesday, maybe. I don't even know what day of the week it is anymore because I'm making things a day ahead of time. So for me, it's Wednesday, but I'm thinking about it as if it were Thursday. So who even knows anymore? I don't know. But so basic premise is we're going to drop these cubes inside this liquid and they are going to fall. So when we have some sort of object in a liquid, we talked about during this review that this object has a gravitational force on it and it also has a buoyant force acting on it. So we have our gravitational force and we have our buoyant force. And those are really the only two forces acting on it. If we kind of do what we've done in the past where we say, okay, let's circle our object, think about what's contacting it, really all that we have is a contact force from the liquid, no other things, no other strings attached. We don't have a normal force, nothing else. So our net force is just going to be Fb, the buoyant force acting on our object, minus Fg, equals mass times acceleration, equals our net force. M times A is our net force. So then what we can do is kind of rewrite things in terms of the full equations. So for the buoyant force, we can say that is equal to the density of our liquid times the volume of our cube times g. And really, instead of volume of the cube, we can think about it as the volume displaced minus m times g. So that's just the weight force of our cube. We're going to assume that every cube has a mass of m. That's what it tells us. It says, hey, every cube has the same mass. Equals mass times the acceleration. And then again, like what we talked about in that video yesterday, so the acceleration, this is not something that we know. But we do know that we can kind of set up this situation where we say, well, our cubes eventually reach this height of 0 meters, and we can start them at different x naughts. And I'm just going to call these x's, just to make it a little bit simpler in terms of our terminology. So we can say that x naught equals x, but whatever. So we have this kinematic equation that says x equals x naught plus v naught t plus 1/2 at squared. In this case, we're going to say the final height, this x, is equal to 0. We're going to call our starting height some height x plus v naught t plus 1/2. And then we know that the acceleration, it's not going to be like g, it's not going to be some known quantity. It's just going to be our acceleration a, p squared. And then we also know, this is just kind of nitpicking, but we know that it's going to be accelerating downwards. We know that we're going to have a negative acceleration. It doesn't super matter, honestly, in your equation, because you know that it's going to sink. But because we know it's going to sink, let's just call this a negative a, just to make it a little bit easier. It won't change like the slope, but it's just something that will make our lives just a little bit easier in saying that, hey, we know that it's accelerating downwards. So in our experiment, we can say that we can drop our cube in there. So we can say x equals 1/2 at squared. So we want to get a into our equation up here. We want to substitute this a for known quantities, or measurable quantities. So we can replace this as 2x divided by t squared is equal to a. Cool. So now we have an equation for the acceleration that we can plug in up here. So rho L Vg minus mg is equal to m, or I guess 2m x divided by t squared. Okay. So then the final thing I'm going to do is, actually this is kind of it for me. This is it for now. So what we have now is something, actually no, we'll do one more thing. So we can say that we really have different cubes that all have different dimensions. Let's call the side of one cube, because it's a cube, it all has the same dimension s. Let's call the side of one of those cubes s. And then let's say that the volume of a cube is just the base times height times the width. So we can say that the volume is equal to s cubed. So let's plug in PL s cubed g minus mg equals 2m x divided by t squared. So now if we're looking at this, this is in terms of things that we can, or not things, quantities that we can immediately measure. Before, yeah, we could measure the volume, but it wasn't immediately measurable with a meter stick, if that makes sense. The side length is something that we could measure, but the volume is something we have to calculate. So we want to keep this in terms of variables that are strictly measurable. So something that we could just come in and say, hey, we measured this one thing. So that's why we replaced volume with this side length, because we want it to be something that we could directly measure, not anything that we're calculating. So we'll come back to this. But as of right now, this is kind of a proof of concept. This is us saying we are able to do this experiment if we are able to figure out the side length of our cube. The mass of our cube is known, the height that we're dropping it from, and the time. So if we think about these quantities, if we think about ways, how can we get S? How can we get M? Well, we know it actually, so we're good with M. How can we get X? And how can we get T? If we kind of walk through these ideas, then we're just walking through our experiment. Our experiment is saying we are able to figure out the density if we obtain these quantities. So now our experiment is just kind of telling us, or us telling somebody else, how can we get these quantities? So now let's come over here and describe a procedure the students could use to collect the data needed to create a graph that can be used to determine the density of the fluid. So yeah, so we're saying if we are able to find these quantities, then we can find the density of the fluid. So let's do it. Let's think about what we would need to do. So we said number one, we kind of have these different cubes with different side lengths. So really the first thing that I would do is I would measure the side length of each of these cubes. So we know that we have this variable s. So I'm going to say measure the side length. Maybe I'll write measure and record, just be a little bit extra with it. Side length s of each cube with a meter stick. So we're being very specific, just kind of short and sweet, saying, hey, this is the quantity that we need. Here's the tool that we're going to use to measure it. Okay? Okay, and then we'll say with the first cube, what I'm going to say when I'm doing this experiment is, because I know the density kind of changes with the volume that's submerged. Not kind of, it does change with that. So I'm going to say for my experiment, instead of like dropping it in from the top, I'm going to fully submerge the cube, and then I will drop it from the fully submerged location. So I'm going to be very specific about what I want. So I'll say fully submerge it, measure the distance that the bottom edge of the cube is from the bottom of the cylinder and call that height x. And then I'll say drop it and measure the time for it to hit. But I want to be very specific about that because I know that density or buoyancy is going to change with the amount submerged. So because that's the case, I want to try to control that. I want to eliminate that error. Okay, so I'll say something about with the first cube, fully submerge it and hold it in the water. Use a meter stick to measure the distance of the bottom edge of the cube to the bottom of the cylinder. So we're saying this is the quantity that we want, and I will define it using a meter stick to measure the distance of the bottom of the cube to the bottom of the cylinder. That's our quantity. Okay, so we talked about how we can get x, and now the final variable that we need is really just this time. So I can say then when, or I'll say measure the time from release, or I'll call it time t, I'll be specific about it. Measure the time t from release to when the bottom edge of the cube hits the bottom of the cylinder. Okay, so then we're measuring the time t. So now we have all of our quantities measured. Now the last piece, something that the College Board really cares about, something that they really focus on, is this idea of experimental uncertainty. So I'm going to say, to do that, that's really just us covering our bases, thinking about what we can do to make our experiment even better. What I'm going to say, again, because we're not doing this experiment, we can be as extra about it as we want. I will say I will repeat steps 2 through 3 with the first cube. I'll say repeat it 5 times to reduce experimental uncertainty. Okay, so I'm going to repeat my experiment 5 different times. Then what I can also do if I really want to go crazy with it is I could say measure and record the side length s of another cube. Repeat steps 2 through 4 with each cube 5 times to reduce experimental uncertainty. So I'm just kind of saying, hey, let's do this as many times as possible. Let's get a wide data set so that we can reduce experimental uncertainty. All right, so now really quickly what we'll do is let's look at the key. Let's look at what the College Board wants. So they say for this, you will get a point if you describe a generally viable method. So our case is viable. We've covered all of the bases. We talked about why it's viable. So that'll give us a point, and that's a very broad point. Like that's hard to be specific about. I would hate to be an AP grader on one of these. 1 point is earned including details about the method that make the measurement parameters clear. So in this case we said measure with a meter stick. I don't know why I just rewrote measure. So with a meter stick, with a stopwatch. Actually, I don't know if I did that. Oh, measure the time t with a stopwatch. So we have to be very specific about what tool we're using and how we're using that tool. So for including details about the method that make the experiment parameters clear, okay? For describing exact measurements to be taken, so that was us saying like the side length or the height from the bottom edge of the cube to the bottom of the cylinder. So we're very specific. We're not just saying measure the height. We're being specific about it. And instead of like saying, oh, measure the time, we're saying the time that takes for the bottom edge of the cube to hit the bottom of the cylinder. So we're being specific. We're not just saying do this. We're saying how are we doing it? For taking more than 2 measurements. So this experiment, it's not possible if we don't do more than 2 measurements. We need at least the height and the time to get that acceleration piece. So yeah, so we need to measure at least twice. So we said x and t, and we also are measuring the side length. So let's just read their example one really quick. So let a cube fall freely through the liquid, hold the cube with one side of the surface of the liquid and release it from rest, let it fall to the bottom, measure the length of each side of the cube, measure the height of the liquid, measure the time it takes the cube to fall a designated distance to travel through each cube. Cool, so that's as simple as we need to be. Ours may be a little bit overly complicated, but I kind of like ours. It's kind of nice, and it's ours, so why not? All right, then for BI. So this one, they just kind of wanted you drawing a force diagram, so I had to change it a little bit because we can't really draw super well on the Google form. So with this, we're saying describe a force that acts, or describe the forces that act on the cube when it's submerged in the fluid. What is the name of each force acting on the cube? What direction is each one pointing? How do they compare to each other? So we know that we have, like we said before, gravitational force, and we have the buoyant force. And because it's sinking, it's accelerating downwards. So we have a downwards net acceleration, which means that Fg is going to be greater than the buoyant force. So that's really all we have to do for this one. This one on their key, it's a little bit different, but really what you're doing is earning a point if you draw a buoyant force upwards, weight downwards, and then just labeling them. So they don't even really have, this one they look like they drew them the same length. But yeah, so all we have to do is label those and draw them up and down. So we've done that, and that's good to go. So then derive an equation relating rho L to the measured quantities in the procedure you described in physical constants as appropriate. Be sure to define the symbols you use. Type the equation below. Show your work on a sheet of paper. You will upload an image, blah, 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 blah. Okay, so we've kind of derived an equation relating rho L to the measured quantities in the procedure that we described. So this is really where we would do this part. So I'm not going to re-derive everything. I'm going to steal this. I made it very messy. So here, what the College Board has been doing for the past few years, and again, I don't know, not the past few years, the last year, and I think it's very helpful, and I think that they'll stick with this. They have you make a table, or they kind of provide a table, and they have you say, they say like, okay, this is the quantity to be measured, the tool, and the symbol. So in our case, we've already done that, but so like we have S, X, and T. So the quantity, we would say one of them is going to be side length of cube. The tool they're going to do for this is a meter stick. And then the symbol, we call that S. For the other one, we said we have the height dropped in liquid. And we said that the tool for this is also going to be a meter stick, and our symbol for that was X. And then we have the time it takes to hit bottom from release. And we said we're going to use a stopwatch for that. And our symbol for that was time. So this is really us just kind of going through. I honestly think they've implemented this table idea just because it makes it easier for them, because kids probably make up random stuff about like their symbols and they're like, what are you talking about? So because everybody has different ways of expressing things, they've made this table to make it a little bit easier for them and us. But so we've done that. So we've defined the quantities that we're going to measure, the measured quantities. We define the symbols to use, and we have, it doesn't say the tool here, but that's okay. Cool, so we've talked about those. And then really, I believe that this equation is good enough because it has our measured quantities along with row L. So I don't think it specifically has to be solving for row L. We'll see what the key says. But it is an equation that can solve for it. So let's see. 1 point is earned for writing an equation related to the forces in the situation. We've done that. We had that row B, or sorry, that FB minus FG. So we've had that piece. 1 point is earned for defining all the symbols that are not given or are not physical constants. So we have defined them. We defined our S, X, and our T. And then 1 point is earned for expressing the buoyant force and the acceleration in terms of measured quantities. So we have done that. So we talked about how we found the acceleration, and we talked about the buoyant force in terms of this rho, and not V, but S cubed. So we've done that. So we've earned our 3 points. So this is their example for it. It's a little bit neater, but we've done it. So if we just kind of redid this portion, this whole derivation, if we redid that down here, then we'd be good to go and we'd have a plus 3 points. So they're very specific about talking about these quantities, how they're measured, and where they come from. So that's a big important piece. So students are to create a linear graph from the experimental data that can be used to determine the density of the fluid based on your experimental method. State what quantity should be plotted on the horizontal axis and what should be plotted on the vertical axis. So this is where it gets a little bit weird and a little bit awkward, and where we kind of have a split in terms of my experiment and their experiment. So what I did when I did this is I said, okay, I'm really my independent variable. I'm picking each cube. So I have like cube 1 has a specific side length, cube 2 has a specific side length, so on and so forth. So I said that really in each experiment that I'm running, S is going to be a constant. So really what I'm doing is my independent variable is going to be the height that I'm dropping it from, and my dependent variable is going to be the time. So what I want to do is I want to set up some sort of situation where my independent variable, the one that I'm changing, is on my x-axis, and my time is going to be my dependent variable. So I'm putting my time on my y-axis. My time, in this case, it's actually time squared because I have time squared up there. But so that's how I'm going to set this up. So I know that I want some sort of, I know that I want a relationship between x and t, and I know that, and t squared, sorry. So I know that I have x and t squared, and because of that, I'm going to have this linear relationship between x and t squared. So I want it to look like this y equals mx plus b form. Okay? So I want this y equals mx plus b form. So what I'm going to do is try to rearrange it so that t squared is related to some sort of slope times my x, so that I can get this y equals mx plus b form. And if I graph t squared versus x, I will have a linearized relationship. So that's going to be a little bit tricky. It's a little bit complicated. Not really, just like algebraically, it's not too bad, but conceptually, it's a little bit whack. And then I'll talk through what they did, which is albeit a little bit easier, but then we don't get to use linearization. So I want to get t squared on the one side. Equals 2mx. And then I will say I got t squared. Got 2m minus mg. Great, so now I have an equation where I have t squared, my y-axis variable, directly, oh, sorry, actually I want t squared to 1 over, this is kind of gross. Great, so now I have t squared, my y-axis variable, is equal to some sort of slope times x, my independent variable. So on my horizontal axis, I could graph x. On my vertical axis, I could graph t squared. And that will give me a linearized relationship because based on our algebra, we saw that x is going to be directly related to t squared. Cool. So this will give us a linear relationship, and now this gets a little bit tricky in describing how we could use the graph to determine the density of the fluid. So for us, it's a little bit hard. So I could say something about, well, what I need to do is I need to find the slope of the graph. So I need to find the slope of the graph, which isn't too bad. That's just a good old rise over run of the x, or t squared. So I need to find that slope. And then I'm going to say, I know g, s for each cube, and m. Solve for, I call it p here, sorry, L, using algebra shown. And I will say, hey, my slope equals 1 over rho L s cubed g over 2m minus g over 2. And I won't do this algebra, but we'll want to get to some sort of final equation where we have this 1 over slope equals rho L s. No, I'm not going to do this algebra. It gets really gross. So yeah, I won't do it out, but get an equation that says rho L is equal to all those things that when we do algebra. So we'll plug in for our known quantities and solve. I spelled quantities wrong. Okay, and then one thing really quickly, or I guess two things. What we can do really fast is we can check our equation. I kind of forgot to mention this. If we drop an object, we know that it follows this equation that says x, like if we're just dropping it if it's in free fall. If we're in free fall and we drop an object, then we say, okay, well, it's going to fall, and we're going to ultimately follow this equation that says x equals 1/2 at squared. So, right, we know it'll be 0, this will look over there, this is negative, whatever. But so this ultimately equation, this falls out if we just have like a ball in free fall. So in air, we're going to assume that the density is really low, so it's about 0. So we can check our equation actually and say if this term is 0, if rho is 0, then our equation turns into x equals negative g t squared over 2, which is what we have up there. So I just wanted to say that really, really quick because I think it's cool and I think it's helpful for us to be able to check our equations. So that was one thing. And then really quickly, again, I don't know why I keep on saying really quick. But so and then I'll say, sorry. And I'll say repeat for each cube and compare results of, right? Because we have different experiments for each cube. So that's what we have going on. And then so what they did actually was they graphed, so they have, they said FB minus FG equals MA. They said A was equal to, what do we find for A? So A is equal to 2x over t squared. So they have rho L s cubed times g minus fg, or minus mg, sorry, equals m 2x over t squared. So what they had for their linear graph is they just graphed So what they did actually was they just graphed s cubed versus a. So they actually just called this quantity a. So they graphed s cubed versus a. So they compared the volume versus the acceleration. Either one's fine, but that kind of doesn't let us linearize. And yeah, so either way works. But so really quickly, let's go in here and check their key for that one, where we are deriving our equation. So describe the way the graph could be used. What they want to see when they're talking about the way that the graph can be used, so all that they want is a point is earned for drawing the best fit line. So, oh, they actually have you draw the graph, my bad. I think, whatever. So we have the best fit line, indicate which property is used for the line. So in this case, the slope. Relate the property to the line to the density. So what they're saying for theirs is they're just finding the slope and then calculating based on the known. So that's what we did too. So that was a little bit long-winded. I'm sorry that took a while. But hopefully it was kind of helpful thinking about setting this experiment, thinking about using what we know, and going from there. So yeah, hopefully that was helpful. And then what I'll do really quickly is just kind of give you a quick Google form with some of your classmates' experiments. They don't have to be the same as this or what was in the key, but I want you to kind of analyze them and see, oh, how does this check out? Would this be like functional? Will it get me the data that I need? Sorry, I guess I'll show myself. Will this give me the experiment that I need, or the equations that I need? Will this be enough to get us rho L? So yeah, so that's kind of what we're going to be looking at now. All right, I'll see ya.